Hello and welcome to this webinar on hardware-in-the-loop testing for electric motor controls. My name is Mathieu Ludac and I am an application engineer at SpeedGoat. Electric motors impact almost every aspect of modern life. They power our vehicles, run our factories, and drive our appliances, which means that they represent a large part of our electricity consumption. And this is driving the need for energy-efficient power electronics and smart controller software. Real-time testing can accelerate development cycles without compromising safety, costs, or quality. You want to test safely without risking damaging precious electrical equipment or prototypes. Test as early as possible to reduce the time needed for iteration loops and thereby your time to market. Improve your knowledge of the system to ensure its compliance with new requirements and regulations. SpeedGoat and the MathWorks motor control test solutions are specifically designed to assist you in this journey. Before we dive deeper into testing workflows, let's look into the agenda of today's webinar. I will first introduce the general background around real-time simulations for motor controls. Then I will focus on our demo, testing an embedded controller driving a virtual permanent magnet motor using Simulink and SpeedGoat tools. I will show how to deploy the motor control algorithm to the device under test and connect it to the real-time target machine running the model of the plant. I will then use this setup to assess the motor controller performance. Deploy a switching inverter model to the FPGA to monitor current and torque ripples and minimize them. Finally, we will test the robustness of the controller by injecting electrical faults to the virtual inverter. Simulink and SpeedGoat test systems let you test motor control designs and embedded controllers end-to-end from a single environment. You typically start by performing desktop simulation in MATLAB and Simulink, which is great to expedite the design of your controls. You can refine your algorithms until you're ready to plug in the real motor for the proof of concept and fine-tune the controller parameters. With Simulink Real-Time, the interface between Simulink and SpeedGoat test systems, you can quickly connect your motor drive and test your control designs against real-world dynamics. Simulink blocks represent the hardware and all its I/O. Placing them in your model and configuring them is straightforward. If you need to change your controller I/O, you can simply do this from Simulink without swapping physical hardware. Experiment without the constraint of an embedded microcontroller. You can tune the controller gains during runtime, perform iterative runs, monitor your controller performance, and even instrument your real-time application with MATLAB and Simulink apps. Switching back and forth between testing the application on target and running the model on desktop is seamless. Simulink will compile and deploy the real-time application onto your test system when needed. Once the motor drive controller boards are made available, it's time to validate PCB layouts, check controller connectivity, and perform functional validation of the controller embedded software. This is the use case we will use in today's demo. Simulink's toolboxes, such as Simscape Electrical, allow you to model your motor with a desired fidelity. If needed, you can accurately capture multiple domains, including thermal behavior, nonlinearities, such as current ripples, as well as high-frequency switching dynamics. Testing an inverter and its controller at full power, typically referred to as power hill testing, requires specific equipment like a dyno bench with the actual motor or a complete vehicle. Instead, you can use SpeedGoat systems for power hill testing, where electrical equipment is operated at full power by emulating components such as electric motors or batteries. SpeedGoat provides a range of power amplifiers to fit your needs depending on the frequency and power operating ranges and integrates them in customized motor emulation racks. These three typical workflows bring many advantages and justify the motivations for real-time testing. You mitigate the risk of experimenting with real mechanical or high-power electrical components, perform real-time testing within a safe and deterministic environment without damaging your precious equipment and prototypes. Being able to isolate your device under test allows you to test earlier in your development cycle, as the other components might not be available, or when the testing equipment is limited, as it is often the case with dyno testing. In short, real-time simulations will save you time and costs. Finally, having a virtual environment has many advantages to test complex or edge cases scenarios, and automate testing, improving your test coverage. Let us now focus on the main subject of this webinar, hardware-in-the-loop testing of a PMSM drive. The hardware setup for this demo consists of a development computer running Simulink, Simulink Real-Time, and an app to allow instrumentation and monitor the tests. A SpeedGoat performance target machine with CAN and FPGA I/O modules. A device under test, the TI Launchpad running the motor control algorithm, and an oscilloscope that is connected to the analog outputs of the FPGA to monitor the motor currents. We set the speed command for the motor in the Simulink dashboard, and it is sent to the controller through the CAN bus. The motor controller would calculate the PWM to control the motor. These signals are read through the digital input and control the gates of the inverter model deployed on the target machine. The motor electric currents are simulated in real time, converted to analog signals, and sent to the controller as feedback. Likewise, the rotor speed is converted into quadrature digital signals. Let's see how to deploy the control algorithm to the embedded controller. Here is our controller algorithm in Simulink. It is a field-oriented controller that will take the speed command from the CAN bus, the position feedback from the quadrature encoder signals, and the currents from the analog to digital converters of the Launchpad. We have inherited the few requirements that we can see by following the links to the requirements editor. In this case, it is a speed limit to avoid the motor from running faster than 5000 RPM, which would damage the real mechanical motor. The blue color in the implementation columns shows that we have implemented all the requirements. For example, the balanced three-phase requirements led us to use Spark and Clark transform, as well as space vector modulation. To deploy the algorithm, you can just click on the Build, Deploy, and Start button, provided that the right controller is connected to your computer. Here, with a simple USB cable. Once the deployment has finished, the algorithm will run directly from boot on the controller as soon as it gets power. The device under test is now ready. We can focus on the SpeedGoat test system setup. First, we will configure the interfaces for an ideal inverter. The ideal inverter will create currents from the duty cycle of the PWM. It does not model the individual gates, and the current will be the average of what the real current would be. As the control algorithm has been designed with Simulink, you can easily simulate it with a model. Here, with the ideal inverter and the PMSM model. To perform hardware-in-the-loop testing, we have deployed the controller to the TI Launchpad, so the algorithm will no longer be of use. But we need to set up the interfaces using the SpeedGoat I/O block set. I'm first going to use the setup block and select the appropriate I/O module. The configuration file defines its functionality as well as the pin mapping for the input and output connection to the real world. It can be changed to suit another test case or application at any time. The duty cycle will now come from the TI PWM output and will have to be captured through the digital inputs of the I/O. We use the dedicated block for this. For the currents, we need to send them to the analog outputs. We first need the setup block, and then link the current in the model to each dedicated channel of the SpeedGoat block. Last, we want the position feedback, and we'll use the quadrature encoder block for this. It directly takes the speed of the motor as an input. We are now ready to run the model. We can use this configuration to verify the deployment of the algorithm on the TI Launchpad and test the real controller performance. We have made a simple user interface directly in Simulink using dashboard components. It allows us to send the commands to the controller via the CAN bus, and we can change the speed set points as well as the speed proportional and integral gains. On the right side, we display the information that the controller is sending back, such as the encoder counts as well as the calculated speed. This is very useful to debug any issues with the controller as well as compare it with values from the model. We can even do some live tuning, and once we are satisfied with the controller, we can start automating the tests. Here I will show you an implementation using the test manager, which is part of the Simulink environment. Our baseline test will compare the result of the hill simulation with the ideal case recorded from a desktop simulation. We use a 10% tolerance in accordance with our requirement. We have also linked the balanced 3-phase requirement to this test, and it will be verified with a logical assessment. Now let's run this test directly from the test manager. Tests can also be scripted using MATLAB scripts or built into the model to run on the target without Simulink. The test manager also stores the results. In the baseline test, the green area represents the tolerance against the reference. In this case, the results are considered as passed, as the motor speed falls within the specified tolerance. For the linked requirement, the verification status now turns to green. The orange color means that the verification test has been implemented but has not been checked so far. We are now satisfied with the basic performance of our controller. However, as we want to avoid any surprises in the final product, we will try to minimize current ripples linked to switching events, which can cause torque ripples in the motor, responsible for noise and EMC problems due to unwanted harmonics. Observing current ripples requires a model of the inverter where each gate is dynamically switching during the simulation. To model this at high frequency, we need to deploy our plant model to the FPGA. For this task, we will use the template included in the Motion Control HDL block set that consists of a model ready to convert to HDL. Let's get back to Simulink. The main component of the template is the green block, which contains the plant model that will be converted to HDL code and run on the SpeedGoat FPGA. The blocks on the outside contain configuration parameters like the motor characteristics. They are placed outside so that they can be modified even after the HDL code has been generated. We note that the input and output ports have been named according to the physical interface that will be set later on: the PWM, the quadrature encoder signals, and the currents. Inside the plant, we find the PMSM model from the motor control block set and the sub-cycle averaging inverter that will capture the PWM signals. The capture will happen at the 5 nanosecond timescale, and the motor model will run with a time step of 1 microsecond. Like the SpeedGoat blocks for the ideal inverter case, we can use the blocks from the SpeedGoat library for the encoder and resolver, which provide optimized code for HDL deployment. In this demo, we will only use the quadrature encoder, but the template is a basis that should suit more cases, and we wanted it to be easily customizable. The simplest way to prepare this plant for the FPGA is to run the HDL Workflow Advisor. The first step corresponds to the target settings. You can choose the target FPGA and synthesize to input any rear plugin, and in particular, for the step 1.3, we can set up the interface parameters. This is where you need to map the input and output ports of the main block to the physical channels of your FPGA I/O. In our example, we have the currents and the quadrature encoder outputs. The next step sets the clock frequency of the FPGA, here 200 MHz, corresponding to the 5 nanosecond capture of the PWM. We need to include the SpeedGoat source for the code modules. The bitstream generation at step 4 can take between 20 minutes up to a couple of hours depending on your machine and the complexity of the model. The HDL Workflow Advisor can also generate a script to automate this process. An example of such a script is included in the template. The last step of the Workflow Advisor will create a generated model based on the source model, but where the main block has been replaced by a subsystem calling the bitstream file. Inside, you can change the output and input ranges. All these steps are also documented in the template and reference application documentation. Let us now copy the generated block into the main model of the reference application for PMSM controller hill testing. Let's first open the model and find the block referencing the included bitstream. We can now replace it with the block generated by the template. Of course, we should not forget to include the new bitstream to the path. Let us now execute a real-time simulation with this high-fidelity inverter and motor model deployed on the FPGA. Of course, we have our controller in the loop. We first see that the currents seem less stable and seem to have some sort of high-frequency perturbation. We can have a look at the currents also on the oscilloscope. We fix the speed to 450 RPM as a reference. Let's zoom in to see the currents in more details. We immediately see that they are very large current ripples. Now let's have a look at the spectrum using an FFT. We can identify the PWM switching frequency at 1 kHz, as well as a lot of harmonics, which could be a problem for electromagnetic compatibility reasons. From Simulink, we can observe the torque ripples from the model of the motor using the Simulink Data Inspector. Torque ripples are a source of instability for the control, but even if your algorithm can deal with them, they might introduce vibration in the system, leading to noise or even premature mechanical failures. There are many ways to tackle such torque ripples during motor control development. We can try to use a different motor, for instance with a higher electrical time constant. Another approach is to have a less stiff current controller. Here, we will simply increase the PWM period. We choose to increase up to 20 kHz as the MOSFETs of our inverter and the PWM generation of the TI Launchpad allows it. We need to rebuild the code for the controller, as this parameter is hard-coded in the firmware. We'll restart the simulation and get back to our oscilloscope. Now we see that the current ripples are drastically reduced and the harmonic content is much cleaner as well. We can zoom in to confirm that we still see a little bit of ripple in the currents, but this should be sufficient for our small set of requirements. Back to the Simulink Data Inspector, we can compare the torque ripple improvement as well. It is not perfect, but much better already. We can also set a test based on this requirement. And now this test has been verified. Electrical faults are an example of test that would be very difficult to execute with a real motor inverter drive, as it might compromise both the hardware and the test setup. Extreme precaution would need to be taken, as malfunction of the scenario at high power could have unexpected consequences. As the inverter model deployed in the template allows to simulate electrical faults, it is very easy to observe the behavior of the current in such a case. Our user interface allows us to inject different faults in the power inverter model running on the FPGA. We can create short circuits in the different legs and observe how our controller deals with them. In most cases, the speed oscillates a lot, but remains reasonably in line with the command, which is a good sign for its robustness. our controller still manages to cope. Now let's check what happens in sinus open loop mode where the current levels are much higher. It will be a basis for a maximum current protection test. We can also check the results on the oscilloscope, and the results are similar. To simulate complex scenarios without modifying the main model, we created a test harness. It uses the signal editor. Here we have created a scenario where the electrical shortage in a branch of the inverter would cause the current to reach the limit value. This will happen 5 seconds into the simulation. Let's run this test. It is linked to our electrical fault protection requirement, as well as with individual limit current assessment for the maximum current allowed in the system. Let's have a look at the results. We see that the fault was triggered at 5 seconds and that the current in the leg A started to increase. But the protection activated and shut off the PWM generation to turn off the inverter currents. Let's see the result in the requirements editor, and we see now that the electric fault protection is now satisfied. Likewise, the maximum current limit is also verified. For further automation, I can use a simple script that will launch all the tests of the project and create a report. This script can then be triggered externally to integrate in your testing workflow. Now that all the tests are run, I can check that the requirements are verified. We have successfully tested the motor control stability, minimized the current ripples, and tested the robustness of the controller. However, as long as the product lifecycle is not over, changes in the controller, motor characteristics, or environment could still cause this requirement to be violated. This is why test automation or continuous integration workflows have become the standard in modern software-driven products. Let's have a look at a workflow example. The control engineer wants to adapt the algorithm to include a new braking strategy. She commits the changes directly in Simulink and pushes them to the source code repository. This will trigger a job on the continuous integration server that will first download the latest firmware, then build it and upload it to the controller. The test sequence will be initiated and the results will be shared with the rest of the team. If you're interested in further leveraging the integration of SpeedGoat with MathWorks and other third-party tools, I encourage you to watch our webinar on automated and continuous integration hardware-in-the-loop testing. It details the integration of the Simulink project with version control tools like GitHub and test automation servers for CI workflows. If you want to reproduce the different steps of this webinar, you can download the 3-phase PMSM with 2-level inverter reference application. It contains a getting started documentation which will guide you to exercise motor control hill. Let's now conclude this webinar. I hope I was able to convince you that real-time testing can greatly accelerate motor control developments at different stages, from desktop simulation, rapid control prototyping, embedded controller hardware-in-the-loop, and power hill testing. Thanks to the powerful SpeedGoat hardware, you can deploy high-fidelity models to maximize the outcome of controller hill testing. You will benefit from ultra-fast signal capture for high PWM frequencies, simulate switching frequencies on the electrical and mechanical domains, and benefit from easy sensor emulation thanks to the SpeedGoat code modules. We have also seen in this demo that SpeedGoat is seamlessly integrated with the MathWorks tools, and you can therefore benefit from the most complete simulation platform. Thank you for your attention.
You want to learn more about real-time controls testing? Then find additional content linked here.